Alright, silly people, here's the situation. We are going to be deriving a recursion relation um, for energy levels of a electron revolving around a proton. Um, so this is a differential equation which involves an auxiliary function, v, um, and this is the ansatz that the book provides for solving this differential equation. Um, and I kind of just rewrote it here to make the derivatives easier. Um, so that's what you got. Let's just start calculating some derivatives. So we got first derivative of this equation with respect to rho. It's going to be just k plus, I better be inside the sum over k of k plus L plus 1 times ck rho to the k plus L. And then the second derivative will be just that same stuff, but multiplied by k plus L now, ck, and then you get a rho to the k plus L minus 1. So let's expand the differential equation using what we got for the derivatives. So we have, and I'm going to use a shorthand where I'm not actually going to write the sum, just make a note that we're summing over k for these. So we have k plus L plus 1 times k plus L. We got ck rho k plus L minus 1. And then we have minus 2 times k plus L plus 1. ck rho to the k plus L, and then in these brackets we have e squared lambda over rho minus L plus 1 over rho squared, and we have ck rho k plus L plus 1, and that has to be equal to 0. So we're going to manipulate this equation until it looks like a recursion relation. So first I'm going to expand this guy out, acting on the rho stuff, and I'm also going to divide everything by rho to the L because it doesn't matter. So that's going to look like k plus L plus 1 times k plus L, ck rho k minus 1 minus 2 times k plus L plus 1, ck rho k plus e squared lambda times ck rho to the k plus, or yeah, just k plus L, minus L times L plus 1, ck rho to the k plus L minus 1. Fantastic. But without the L's. Now it's fantastic. Now we're going to collect the terms that have the k minus 1 factor. So we have k plus L plus 1 times k plus L ck, but also minus L times L plus 1. That is multiplied by ck rho k minus 1. And then we have minus 2 times, actually just minus ck rho k. We have e squared lambda minus 2 times k plus L plus 1. Cool. So what I'm going to do is I'm just going to take this left term and add a 1 whenever I see a k, right? So that will fix the equation. So we'll have k plus L plus 2 times K plus L plus 1 minus L times L plus 1. We have CK plus 1. We have rho to the K minus CK. And then on the right hand side, I'm just going to keep everything the same. And it should be plus minus 2K plus L plus 1. Cool. And now I'm just going to solve for CK plus 1 over CK, which is going to look like minus sign, so 2k plus L plus 1 minus e squared to the lambda, e squared lambda. And then k plus L, gross, plus L plus 2 times k plus L plus 1 minus L times L plus 1. All of that down here. I also canceled out the row k's. But yeah, I think that was what was in the book. Yeah. So that is 13.1.11 proved. Now I need to look at proving 13.1.14, which is a few lines later. So the point of this recursion relation is that the ratio is equal to 0 when 2k plus 2 times k plus L plus 1 is equal to e squared over lambda. Makes sense. So you're going to solve the lambda then for, you're solving for lambda, so you're just saying e squared over 2 over e squared times k plus L plus 1. And then lambda is also equal to, by definition of a different equation, 13.1.9, is just the square root of 2m over h bar squared w, where w is the work. And so when the recursion ratio is equal to 0, that's the point of time where your energy is entirely in your potential, so it will be equal to minus work. So E equals minus work, and then we just solve this equation for work. 4 over E fourth times k plus L plus 1 squared. You'll divide by 2m. You'll take the inverse and then divide by h bar squared. So, okay, simplifying that, it's going to look like 2m e fourth minus sign, and then divided by 4k plus L plus 1 squared h bar squared. And then the 2 will be reduced to 1. So you got 2 times k plus L plus 1 squared h bar squared, which is equal to your energy. And that is a proof of 13.1.14. So there you go.